Sir Michael Berry is one of the greatest physicists in the world.
Physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things.
He is a recipient of the Lawrence Medal, the Dirac Medal, and the Ig Nobel Prize.
We stand on the shoulders of giants. I've been working a long time on what people say is the most difficult, unsolved mathematical problem.
He is the originator of the Berry phase, a cornerstone of quantum mechanics.
Quantum physics democratized music.
That's why physics is like sex?
Yes, indeed.
Objective truth from the point of human brain doesn't exist.
Yeah.
What the magic mirror is.
Wait.
Yep, it's amazing.
Every advanced technology is indistinguishable from magic.
How quantum mechanics democratize music?
Think of a CD player. We used to use it not too long ago to reproduce our music, to listen to our music. In the CD player, which was invented in the early 1980s, is a laser, which monitors the spinning disc with its little bumps and pits and converts the recording into electricity and then into sound. Right, it's a laser is at the heart of it. Now, the laser was invented in around 1960 by people who had no idea that 20 years later, engineers, different kind of cleverness, would use the laser to reproduce music. I remember as a student in the early 1960s, we saw lasers, we were amazed by them, and they were described as an invention looking for an application. Nobody knew what to do with them, but they were beautiful. Now, those physicists invented the laser using a principle that Einstein had discovered in 1918, groping towards quantum mechanics and trying to understand the different ways in which atoms interact with light. And he realized that for consistency with existing physics, even though he didn't have the full quantum mechanics, there had to be an additional mechanism, which he called stimulated emission, that an electron in an excited state could be stimulated by light passing by to decay into its ground state and therefore emit a photon. Now, it's that stimulated emission which led to the laser. But Einstein himself never imagined that 40 years later, people would use his idea to make the purest, brightest light. So there's this chain of connections involving people with different types of genius. Now, the CD player was the first device by which humans could hear music essentially perfectly reproduced anywhere. There was the Sony Walkman, but that was slightly awkward. It was a tape and you had to decide exactly where to start and stop it and so on. But the CD player, little player, you could go anywhere. You could be on the ocean, you could be in the mountain, in the forests. You know, there was the gramophone, but then you couldn't carry that anywhere. There was the radio. You couldn't choose what music to hear. So the CD player democratized music. Anyone, anywhere in the world, could hear music perfectly reproduced without having to go to a concert or so on. But it's a quantum physics machine. I explained that. It goes back to Einstein. So quantum physics democratized music.
That's why physics is like a sex?
Yes, indeed. Indeed, as Feynman said, it has consequences, but that's not why you do it.
Which the most surprise link you've ever found between music and physics, quantum world?
Well, just this one that I mentioned, the CD player. I mean, there are all kinds of connections. You know, people make electronic music, they create music based on mathematical themes and so on. I do something related but actually different, which I call ear math. And that's the following. Not taking natural sequences of vibrations or whatever and listening to them, that's sonification. It's used in genomics. It's used to listen to sequences. It's used in astronomy to convert some of the signals into, because hearing is different. No, what I'm doing is a little bit different. It's taking quite advanced mathematical objects, things called random matrices, doesn't matter what, and instead of looking at their graphs, because vision is very important. I mean, a lot of science, especially mathematics, you understand if you draw pictures of something. But we also hear, and hearing is different. So the idea was, if we listen to these mathematical constructions and creations, can we hear things that are less easy to see? Because although hearing is restricted, it's only one-dimensional, it's a sound, whereas seeing is several dimensional. We also have colour. Hearing is also more sensitive in some ways. And the answer is sort of. I mean, we could distinguish similar looking mathematical functions by their sound. So it's not quantum, nothing to do with quantum, which was your question, but it's the best answer I can give related to something that I've done. So I haven't thought seriously about music and mathematics. It's a huge subject. There's a great deal written about it and much wisdom, but not by me.
Can we say that gold, it's not gold? That's only our imagination how gold looks like?
Well, it involves two things. It involves the physics of how light is absorbed by the crystal structure of the gold, and of course different frequencies of light, which we see as different colours, are differently absorbed, and what we see is the light that's not absorbed. And it's the light that's not absorbed in gold is sort of yellow-ish, yellow plus shiny. But the fact that we see yellow involves the way in which we see. I mean, we only see a narrow region of the spectrum, and we have only 3 kinds of cones in our eye. So although infinitely many different frequencies hit our retina, only 3 numbers go to the brain, the way in which these 3 cones are excited. And it's the yellowish one that gets excited with gold. So the colour of gold, it is physics, but the way we see it involves our physiology. No, the surprising thing about gold is that it took a long time for computer calculations of absorption of light in solids to be sufficiently precise to make a prediction from Schrödinger's equation as to what colour would emerge from gold when you shine white light on it. And when the calculation was done in the 1990s, the answer that came for the colour was silver. Well, clearly something has been wrong with the modelling. And what was wrong was physicists hadn't taken account of the fact that gold is heavy, so the electrons which are responsible for the absorption and emission of light move fast, so fast that you have to include relativity. So as well as quantum mechanics, you have to include relativity. So it's not the Schrödinger equation, it's the Dirac equation, which is the way to incorporate quantum mechanics into relativity in this class of situations. Dirac, by the way, the most brilliant intellect that the city where we are now, Bristol, where I live, has ever produced. He lived not far from here, was born. So the amazing thing about gold is that it's quantum, but also relativity that we see with our eyes.
It sounds like a proof that objective truth from the point of human brain doesn't exist.
Yeah, I agree with that. And I have a little meditation which I called True But Not Real. And this came because I'm interested in visual illusions. I give a whole talk about aspects of visual illusions. And one of them is the mirage. The mirage is an illusion because you think you see water on the road or a mirror, but no, it's refraction. It doesn't matter. It's an illusion. And I saw a book advertised about mirages, and I thought, I will buy it. It looks interesting. This book was not about the physics of mirages, as I had thought. It was about the history and culture of mirages in different parts of the world. Very interesting. And the author quotes a Buddhist phrase that the mirage is real but not true, meaning we see something. We really do see something. We have a perception, that's real. But the way we think about it as being a mirror on the road, it's not true. There's no mirror on the road. There are many such. When you look in a mirror, you see image of yourself behind the mirror. There's no copy of you behind the mirror. Indeed, there's nothing behind the mirror. When we look at a television, there are no little people inside the television, but we think of them as real. So I thought, real but not true. With physics, it's sort of the opposite. And that's why I wrote this little bit. It's true. We do our experiments. We make our inventions. They work perfectly. I mean, imagine all the camera, the optics being used now, the electronics. Of course, if it wasn't true, nothing, it would never work. It's obviously true. It's most impressive. These are the most impressive feats of creation almost that humans have produced. But if you ask, is it real? That's a real can of worms, because it depends on the level at which you're trying to understand something. And I often, as a challenge, say, how do your glasses work? I'm wearing these spectacles. Well, you say what you learn at school. The rays come in, they get refracted onto your retina, you get an image of what's outside. Okay, and that's quite convincing, and it's used in optical technology, design of glasses and so on, computer calculation of all the rays. But then along comes a physicist like me. But rays aren't real. Light is really waves. Rays are convenient constructions, approximations. That's when the wavelength is very small, but really light is waves. Well, that helps you understand some details of what's happening in the image, how there's a limit to the resolution and so on. And then another physicist comes along, who could also be me, and said, oh, but just a minute, these waves are really electromagnetic fields. You should start from Maxwell's equations. Then comes another physicist and said, no, the fields aren't, they're quantum fields. They just give you the probability of detecting photons. Now, so you say, oh, which of these different levels of explanation is the real one? The answer is all of them and none of them. Because, you know, there's always a deeper level. If you ask some fundamentalist physicists, they say, oh, it's the quantum level. But that will only be the basic level until the new physics is discovered beyond the quantum. So the explanation of something, which we, in our common language, we say it's how things really work, is to be understood at different levels. And there are different levels which are appropriate for different phenomena. So with your glasses, certainly it's the first one, the geometric optics, is the most useful. But if you want to understand the deeper physics, then you go through the cascade of levels: rays, waves, electromagnetic fields, quantum fields. And but you pay a price by going to this deepest level, deep that we have now, because the deeper you go, the farther you are from the phenomenon. And I often say to people who work on fundamental physics, as they call it, starting from the equations of quantum electrodynamics, directly explain how your glasses work. And they can't do it. You have to go through all the levels. So this is my take on true but not real.
Is quantum level the deepest?
Well, that we have now, yes. But you know, we've been doing science merely for a few hundred years. We're a little species on some remote planet in some insignificant solar system somewhere. It's ridiculous to think that from this limited perspective we've reached the deepest level of understanding what's in the universe. Because I can't prove this, but it goes against all history and against all culture. You know, we know a little bit more than dogs. They don't know quantum mechanics. They can smell better than we do, so they can navigate aspects of the world that we can't. But so we know a bit more, and we're very proud of it. One reason why we've achieved so much, even though it's still limited, is that we've learned not to do it alone. I mean, science is a cooperative enterprise. We, of course, some people compete and you get prizes for this and that, which is fine. It's natural human enthusiasm. But, you know, everyone, Newton, we stand on the shoulders of giants. That's still true. And so we've learned somehow to combine our individual inquiring minds into a kind of group mind. I mean, science is the closest that, other aspects of culture, music too, that humanity has developed into what we could call a group mind. I mean, we're all separate little minds and brains, but we all learn from each other. And this is why we've achieved so much. But still, even as a species, there's a limit to what we can, what we're capable of. And all the talk about AI, about which I know very little, by the way, is that, well, this might eventually surpass us. And there's no reason in principle why it can't, because, as I say, we are limited.
Do you believe that something deeper than quantum level
Yeah, of course.
can exist?
Of course. And I mean, one obvious place where we might encounter this, although we can't do experiments yet, is where quantum mechanics meets extremely strong gravity. And that, in the middle of black holes, for example, or in the early years of the universe, and when you are in a regime where you both need quantum because things are small, and you need relativity because gravity is intense. So that's one way in which some deeper synthesis, which has not yet been found, might be important. I mean, people speak about string theory, which, unfortunately, yet it hasn't led to any experimental confirmation. But suppose it does. Well, it's still quantum mechanics. It's a very sophisticated quantum field theory. So it isn't what I'm imagining, that eventually there'll be a way of understanding which is much deeper, and it will be conceptually more subtle than we can appreciate or anticipate at the moment. It could be. Well, quantum mechanics itself, when it was invented in the 25 years from 1900 to 1925, was driven all the time by experiments. I read a biography of Heisenberg. Almost every week there were new experiments which he was wrestling. How can these be incorporated? And new experiments on absorption and emission of light and chemical reactions and so on. We don't have that now. We don't have experiments that contradict quantum mechanics in the way that those early experiments contradicted classical mechanics. So we don't have that guidance, which is a pity. I mean, one day there will be some experiment that will definitely contradict quantum mechanics, but at the moment there aren't any.
Can such controversial theses expose physics to the charge on being unfalsifiable?
No. It's perfectly falsifiable. We do experiments, they could turn out wrong. I mean, if the physics was wrong, none of the technology in this room would work.
What inspires you to connect quantum physics and diverse examples like magic mirrors or Riemann zeta function?
I like connections. It's interesting to ask where this comes from, and it's one thing to do physics. It's a different thing to understand how you're doing it. That's a sort of philosophical or neurophysiological job. But I've been heavily influenced by the culture of the physics department in Bristol, where I have been for just 60 years now, because there was it was never explicit until a certain moment, which I'll tell you, but it was implicit in many of the work that people did, and in particular, a previous director of the department, Charles Frank, who de Gennes thought should have got the Nobel Prize with him for liquid crystals and many other things, in his retirement speech, he said, physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. And that had a big impression on me when I heard it nearly 50 years ago now, because I realized that I'd been doing this without really thinking about it. And I like connections. And one was that in the beginning, I was studying connections between quantum and classical mechanics. That's some of my early work, in connection with certain experiments that were being done on the scattering of atoms and molecules from one another, which are quantum but nearly classical in some cases. And after some time, I realized that quantum mechanics is a wave theory in some of its manifestations, but there are other kinds of waves, in particular optics, And you can see with optics what you're studying. And so, as well as doing quantum mechanics, I became interested in optics because you can, as I said, see the phenomena you're studying. There are counterparts of different types of quantum phenomenon in optics. So that's a low-level connection. But there's another one between different types of waves. You see, one of the areas that I clarified early on was focusing of light and quantum waves in situations where you're very far from the symmetry that you have when you want to discuss the focus of a lens, which is a point. Typically, focusing occurs on surfaces in 3 dimensions. They're called caustics. They have a name. The name comes from burning glasses, patterns in the sun. Okay. And that physics we revolutionized in Bristol, ancient physics, hundreds of years, because of new mathematics, something called catastrophe theory or singularity theory, developed in Russia and in France in the 1960s and 70s. We realized it applies directly and we could predict new things and understand. Now, not only could we understand this focusing, but what waves do very close to it. The pioneer in this, although he didn't realize how general it was in 1838. Airy understood the type of interference you see in rainbows when all the raindrops are nearly the same size. Then inside the rainbow, you see a number of fringes. Okay, good. Well, I understood this and did some work on it as well. But then I realized something else. If you have a boat, a ship on the water, moving, you see this V-shaped wake behind the ship. Now that V-shape is a caustic of the rays of the water waves, okay? And I realized something, that decorating it, you see across these V-shapes, you see some waves. It's exactly the same wave function, mathematical object, that you can see in rainbows. Now imagine that you're in a small boat on the water and a big ship passes by. After some time, its V will reach you and you will go up and down like this. You are then feeling in your body exactly the same mathematical object that you see with your eyes when you look in the sky and see these interference fringes inside a rainbow, which, you, as I say, you see under these occasional circumstances when the raindrops are similar size. So that was a connection, and I like that. You feel in your bone, in your body, the same mathematics that you see with your eyes when you look. So this is one example, and I don't know, I like these connections, and I think the world is connected. And this example you asked me about, which is quantum physics democratizing music. I mean, think of the connection. There's Einstein, pure theoretical physicist. They're the experimental physicists who created the laser. They're the engineers who then realized you could make a machine for producing music out of it. And then, of course, to make their vision into a reality, you need electrical engineers, you need acoustic engineers, you need fine-level mathematics, you need business, you need advertising, and of course you need music, because you have to have something to reproduce. So the world is connected in wonderful, interesting ways. And I like it. If you ask me why I like it, I can't tell you.
Maybe I should ask you before what the magic mirror is.
Wait. It's something invented in the Han Dynasty 2,000 years ago. It's a mirror. You can see your face in it. Yep. It's a mirror. On the back of the mirror is a pattern, a deep cast pattern. This is bronze cast, polished mirror. Why it's called magic is because of a feature which those people who invented it probably didn't understand, didn't anticipate. It wasn't designed in. If instead of looking in the mirror, you shine a light on it, or the sun will do, and look at the reflection on the wall, you expect to see a circular patch of light, which you do see. But in that patch, you see a ghostly image of what's on the back of the mirror. It's a very...
How does it work?
Well, I'll tell you in a moment. There you can see it on the back.
Yeah, it's amazing.
It's an amazing thing there. Now, when China, 2,000 years ago, those mirrors migrated to Japan, and they had a religious significance, and they were brought to the West in the 19th century, and physicists were very puzzled by them, wondered how they worked. Now, it was quickly realized, or guessed, that during the process of cooling and vigorous polishing, the release of elastic stresses means that the pattern on the back is very weakly reproduced on the front, too weakly for you to see. But that left an unsolved problem, which I solved about 20 years ago here. How is it that undulations that you can't see when you look in the mirror produce such a dramatic picture? Now, I was shown this mirror by a colleague, and I was very astonished by it. Really, I worried, how could this possibly be? And the optics is a rather unusual regime. I thought that because I had been studying focusing and caustics, these sharp lines, for example, the lines you see on the bottom of a swimming pool in the sunlight, these patterns are caustics produced by the focusing of sunlight by the wavy water. I thought this would be something of that kind. That was wrong. Those undulations are too weak to produce focusing, but they do produce concentration. It's what we call prefocal brightening, which is an area of optics that hadn't been understood. It's remarkable because it's actually not very complicated. And then you could predict what the image would be. And one particular feature that you predict is that, which I didn't show you here, it takes more time, but it's that each step on the back, reproduced on the front, produces a line that has both a bright and a dark side. This was a prediction which indeed is true when you look. You can compare. And when I had this theory, I took some pictures with my digital camera, another quantum device, by the way, that makes theorists like me able to do experiments, put the file in my computer, scanned across the image, and could check against the theory and realized that the heights of these undulations is about the same as a wavelength of light, much too small for us to see. So this explained the theory. It's an amazing story. I mean, it goes back 2,000 years, and next month, I will be in Japan for a meeting on Oriental magic mirrors. And there will be people there from different areas of art and science, and there'll be an engineer there who has used this phenomenon to test the flatness of semiconductor wafer surfaces. Instead of trying to look in with a microscope and trying to see, you just shine light on the ceiling. You immediately see if there are any defects in the surface.
It's a great example that, that's something more than, I think, magic mirror. It's like a proof that magic doesn't exist. Only our understanding physical phenomena
and it's a very
exist.
Well, exactly. It's a very simple example. And they were called magic mirrors because, of course, they had no understanding of laws of reflection and concentration, and they didn't intend to build it. I mean, this is made for tourists, of course, but in 2,000 years ago, this was an unintended consequence. By accident, they would see, they didn't have bright lights like we do, by accident, they would see, carrying the mirror outside, the reflection on the wall, they would see this structure. And naturally, they called magic. Arthur C. Clarke made this wonderful statement: every advanced technology is indistinguishable from magic. Of course. These little phones we carry around, or suddenly we talk to somebody on the other side of the world. When we were children, this would have been unimaginable.
All mysteries are proofs of our understanding.
Yeah, we are limited and we make progress, and sometimes we anticipate things, predict them, but mostly we try to understand things that already exist. Sometimes we succeed, sometimes we don't exist.
Mystery of human consciousness also?
Well, that's a problem at a much higher level than the little physics that I've been speaking about, but yes. What does it mean for a machine, a biological machine, to be conscious of itself? Okay, and there's of course vast...
Let's talk about that fundamental physics.
Yeah.
Do you have any opinion about free will?
Again, the critical word is only, and because that implies understanding whether machines are only machines. Don't forget that they're created by us. So it's a bit subtle what machines are. Of course, when we teach engineers, we teach mechanics and machines how they operate, but we tend to incorporate the fact that we made them.
Our consciousness made them.
Well, our hands and our conscience and our imagination made them. Now, as for free will, this is complicated. I don't have anything really original to say, except this, possibly. If we know what somebody is going to do and what they're going to choose, and they don't know, they would still say they have free will. Sometimes I can predict when my cat will come and demand food. But she's thinking she's choosing when to come and demand food. But we know better. And sometimes with other humans, we can predict what children are going to do. They think they're doing something freely and choosing. So it might depend on the relativity of levels of consciousness of organisms. I don't know if that makes any sense, but it means that free will isn't something that's absolute. It's something that depends on the perspective of the person who is acting as though they have free will.
Maybe we are not capable of understanding such questions.
Well, we may be capable of understanding them, but we just don't understand them yet. We are complicated organisms, and we interact with the outside world in different ways, and we have this amazing connectivity of neurons, which somehow is responsible for our complexity. Whether we'll understand, whether this machine can understand itself, is an interesting question. I don't know the answer. So I don't say we will never understand consciousness. It's just we don't now. And it's the subject of intense speculation and neurophysiology. The difference is we can actually look and see what the neurons are doing when we think we choose. So I have nothing really to say about this. I mean, I'm a physicist. I do my little calculations, which I enjoy. And so I can't really say anything intelligent about consciousness.
Is the berry phase the biggest discovery?
No, I liked it. It was a little calculation, which I did. But it's not the thing I'm pleased about it, and I'm surprised that it's so widespread in different areas of science. My colleague John Hannay, who discovered later the classical counterpart of this quantum, he said, when I told him about this phase, he said this would be very important, and I didn't think so. But it turned out, but no, I mean, I've done other things that I've been more, it's given me greatest pleasure, and I've thought more unusual, and especially things in mathematics. You see, I'm not a mathematician, but some things that I've done in mathematics of divergent series that apparently you would think give you an infinite answer when you should get a finite answer, but it's actually ways of making them meaningful. I solved a problem in divergent series which had been around for 150 years, and I was very pleased, 120 years, and I was very pleased with that. So, what pleases me is sort of almost a private matter, but I'm just telling you, since you asked, that I don't think the geometric phase is the best thing, but it's a good thing.
But what the berry phase is?
Well, the way I think about it now, it's an unexpected, at the time it was, application to quantum physics of some geometry which is subtle but known in other contexts. For example, if you drop a cat upside down, she will land on her feet. Now, how can she do that? Because to rotate, she needs angular momentum, and she has none to start with. And there's no way she can acquire angular momentum from the air is insignificant. She does it because she can twist her body in a clever way, different parts moving in different moments of the trick that she does, so she can turn without ever having rotated. Now that's a wonderful thing. Now here's another piece of geometry. When you try to reverse park your car into a narrow space, a small space, you perform a maneuver and then you find you're rather far from the curb. If you don't do it right, it often
I
happens.
don't really like it.
Yeah, in real life. And then you perform a series of maneuvers. Now, each of these is a little periodic maneuver. You go back, you turn, and then you drive forward. You turn and you drive forward. After each maneuver, you yourself are in the same situation as you were before, but the car has moved sideways a little bit. It's a counterpart of the cat's turn without ever having rotated. You have to perform a rather large number of these maneuvers, very often, more than you expect, if you don't park very well. Now, that geometry has a name. Something returns, but something else doesn't return. So you, in the car, are exactly in the same situation with respect to the car as you were before the car. But the car has moved. The cat, her body is the same shape as when it started, but it's now upside down. Now there's a phenomenon, it has a name, it's called anholonomy, it doesn't matter about the name. Now it turns out that something similar, this is what I realised, something similar happens to quantum waves when you change the state of a system, change the magnetic or electric fields that act on a particle, or you change polarized light, the angle, in such a way that features that you change are the same as before. Magnetic field on a neutron is the same as it was when you started. And then you ask, what happens to the wave? Now, waves keep waving whatever you do, even if you do nothing. But I found that there's a little extra contribution to the phase of the wave, the stage of its oscillation, that depends on the history of what you've done to it. And this is exactly mathematically analogous to those two examples I've described from familiar life. So it's as I said, an example of a little effect in quantum mechanics that reflects this kind of geometry with which we're familiar but not very familiar in everyday life. And we're familiar without thinking about it, though mathematicians understand it well. So this little thing in quantum mechanics, I didn't expect it to have the applications that it does have, and I'm not terribly interested in them because my interests move in different directions. Once I've discovered something, I move on to something else. Now, there are physicists, and I respect them, who spend their whole life doing one thing, going deeper and more applications. But I'm not such a person.
Do you remember the moment?
Yes, I do remember the moment. I will tell you two things. First, the moment, and then about moments of discovery. About the moment, I was giving a lecture in Georgia Tech about an early version. It wasn't really the geometric phase then. It was to do with quantum chaos, and I needed to understand a particular class of arrangements of energy levels. And I said, this particular phenomenon applies when you, for example, have no magnetic fields. Something changes sign. I didn't think of it then as a phase change of 180 degrees. That's a change of sign. I didn't think of that. And then somebody in the audience, Ron Fox, said, well, suppose you do have a magnetic field. What happens to that change of sign? And I said, well, that moment, it will change the phase of the wave in some ways. I will tell you tomorrow. So I went back to my hotel room and I realized it was difficult. I didn't understand it. And I went back to Bristol. It was several weeks before the full phase came out. But it came from that question, that one question. Now, whether I would have found it, if that question happened, is an interesting question. I can't answer it. But I was well prepared because, as I think, was it Pasteur? Chance favours a prepared mind, right? Because I'd been working on phase different ways for a number of years. The first paper I ever wrote as a student was a paper best forgotten now, was about aspects of phase. So I was primed to think about phase, but anyway, that question was the trigger. Now, on sudden discovery moment, of course, that's what we seek all the time. And I have a name for these moments. I call them claritons.
Claritons.
That's the elementary particle of sudden understanding. It's the one elementary particle that I've discovered. You see, you can say, okay, people have spoken about this, Archimedes, Eureka, or the aha moment, but there's more with the claritons, because there are also anti-claritons that come the next day when you realize that what you thought yesterday was wrong. So understanding is a succession of clariton, anti-clariton, annihilation events, and you hope at the end is a clariton remaining.
If you, Sir Michael Berry, could find answer for one single question about the reality around, what it would be?
I was at a meeting in China a couple of years ago, and there was an event where a number of us physicists were invited to the public event to describe what we think of the most important unsolved problem in physics. Right. Now, of course, my colleagues there, they said, and it's quite correctly, we want to understand something deeper beyond quantum mechanics, or we want to understand dark matter, or understand dark energy. And I agree they're important problems. But I suddenly had a moment of intuition. I said, one of the things that we like to claim is that quantum mechanics explains all of matter. When Dirac invented his Dirac equation, he said, with this equation, we in principle understand all of chemistry. It didn't put chemists out of business, but still we now know that quantum chemistry is very important. Okay, now matter. But I said, but think about it. There's something very unusual about the matter in this room. Much of it is alive. Where is aliveness in quantum mechanics? You know, where is it? Now,
maybe in the complexity.
Well, hang on. Now, see, Schrödinger wrote this very influential book, What is Life? He didn't, his actual suggestion wasn't quite right, but it was enormously influential. Quantum biology, now being studied, a very important subject, but different, because there, and Jim Al-Khalili, who I've mentioned several times, is now involved with this subject. The idea is to take a particular biological phenomenon, photosynthesis, or the way in which some birds can, with magnets in their heads, detect direction, and understand whether this biological phenomenon depends on quantum mechanics, whether it would happen anyway and quantum mechanics helps it or quantum mechanics hinders it. This is a very important subject.
How matter is transformed into life matter.
But it doesn't address the question, where is aliveness itself? See, quantum mechanics, the way we think about it, is a quantum object, even the simplest living object, lives in something we call a Hilbert space, some mathematical arena where all the things that can happen quantum mechanically are located in our minds, in our formalism. But where in that formulation, where is aliveness? It must be there somewhere. We have no idea, absolutely no idea. So if you ask, what would I like to see solved? I would like to understand that. As well as, in a different world, I would like somebody, it won't be me, to prove the Riemann hypothesis, or to prove that it's false. Because that's called a hypothesis, because it isn't known. Most people think it's probably true, but one of the reasons why it's so difficult to prove could be that it's not true, and that somewhere very far in this set of numbers, beyond any computer, there's something that violates this prediction. So I would like to understand that, but also, where is life in quantum mechanics? Aliveness. There may be degrees of it, it could be an electron has a tiny bit of it, insignificant.
Maybe liveness, it's out of quantum world, or it's deeper.
Well, I don't think so. I mean, when I speak about going beyond quantum mechanics, I don't think that will be because there's so much in quantum mechanics that we're still discovering within quantum mechanics, all of quantum information theory, so fundamental now, and so such an active subject. Continually discovering things within the quantum mechanics. So, my CD player, that's an example. That's in quantum mechanics. Took a long time to find it. Even Maxwell's equations. I mean, there's a huge amount of classical objects and signal processing theory, and so new ways of distributing signals down power lines and optical fibers, continually being discovered. New qualitative phenomena hidden in Maxwell's equations. So I don't think life is of the type like the middle of a black hole, where you know that quantum mechanics has to be changed. It is quantum mechanics, but our theories are cleverer than we are.
What new ways made quantum computing transform music creation, sharing?
Good question. I don't work on it, and so I'm not going to say much, but I'll just say one thing that disappoints me. And when I first heard Arthur Eckert talk about this many years ago, I made this point to him. I admire
Polish scientist.
Yes, indeed, the Polish scientist Arthur Eckert. Very important contributions. His contribution was to understand how quantum mechanics would transform cryptography. And my response was, well, of course this is important. I don't want people to get access to my bank accounts and military secrets. But it's a negative thing for humanity, the keeping of secrets. It's an unhappy thing. And I appreciate I have a key to my door, which I use, leave the door open. But still, it's not a life-enhancing thing. And sooner or later, there will be applications of quantum information which are life-enhancing, but we don't know what they are. And any attempt to predict is almost always wrong by people like us we're not engineers. Einstein would never predict the CD player, a life-enhancing application of quantum mechanics. Or the fact that the color of gold, which people have seen since ancient times, is a combination of quantum mechanics and relativity
And human brain.
Yeah, well, quantum mechanics and relativity are creations of the human brain. They're our formulations for understanding things at different levels. Quantum information will transform the world because ordinary quantum mechanics already has. Leon Lederman estimated, this was already a number of years ago, that 1/3 of the gross national product of the entire industrialized world depends on, in one way or another, on quantum mechanics. Silicon chips, lasers, whatever. Medical radiography, huge numbers of...
Is for you AI hype or hyped?
Well, it's probably a bit of both, but I have the same reaction to this as I have towards string theory. String theory is, let me tell you why, is described as, by its enthusiasts, of definitely the theory underlying quantum mechanics and gravity. And there aren't... Well, okay, I'll tell you. Many years ago, I met John Schwartz, one of the creators of string theory, before Ed Witten became involved at Caltech. And I was very impressed and very intimidated by the extreme cleverness of these quantum string theorists. And he met me and he said, "What are you working on?" I said, "Well, I'm trying to find a connection between quantum mechanics and the Riemann zeta function, in Riemann hypothesis." And he said, 1985, "We have lots of zeta function in string theory. I expect the Riemann hypothesis will be proved in a few weeks. It'll be a baby exercise in string theory." 30 years later, I met him, 25 years later, and 30, and I reminded him, he said, "Oh, did I say this? We were very enthusiastic then." Now, you could say that was hype, like AI, but I think it was natural enthusiasm of people who they have a new idea and a new framework, and they make claims which are probably going to be exaggerated, but what they do will have some influence and some effect. So there probably is hype, and both hype and hyped, but still there is a solid intellectual core there, which will change society in ways which are at the moment hard to predict. So I think keep a calm head, but understand people's enthusiasm. Or in the case of Geoffrey Hinton, unenthusiasm.
Thank you for your time. It was an honor.
Lovely. Thank you very much. I enjoyed it enormously.